Hello, I'm Abhay Agrawal. I am a member of technical staff at Nutanix. I work for Nutanix Kubernetes platform team, where we build Kubernetes solution for enterprises. Today, I'll be covering some core topics, core fundamentals of Kubernetes. So let's start with CAPI, which is Cluster API. So what exactly is Cluster API and why does it matter, right? So Cluster API as a Kubernetes project. Cluster API is an official Kubernetes sub-project under CNCF. It's been around since 2018 and has matured significantly. It's now used by major enterprises worldwide. The core idea is brilliant in its simplicity. If Kubernetes can manage application workloads declaratively, why not use the same approach to manage Kubernetes clusters themselves? Lifecycle automation. CAPI automates the entire cluster lifecycle, and I mean everything. Creation, scaling, upgrades. The most painful operation becomes simple. Change the version number, and CAPI orchestrates the rolling updates. Deletion can remove can remove all the resources, clean removal of clusters with proper resource cleanup. The features of CAPI are CRDs to represent cluster machine and machine templates and infrastructure resources, and it is declarative, consistent definition of clusters across providers. So cluster resource definition. CAPI extends Kubernetes with new resources types using CREs. You get familiar Kubernetes resources like cluster, machine, and machine deployment. These works just like pods, deployments, and services. Same kubectl commands, same patterns. For example, if you want to get your cluster, just you type kubectl get clusters. It shows your managed clusters. You want to scale up your machine deployment, just type kubectl scale machine deployment, your machine deployment name, set up replica, and scale your cluster. Declarative and consistent. This is the key difference between traditional infrastructure automation and CAPI. Traditional approach, run Terraform scripts, hope they work, maintain separate state, right? CAPI approach, declare your desired state, CAPI continuously reconciles to match it. Someone manually deletes a control plane node, no problem. CAPI detects it and provisions a replacement automatically. Self-healing infrastructure becomes the default and not an add-on. CAPI is an API-driven model. The same pattern you use for managing applications now work for your infrastructure. Your team already knows kubectl, YAML, and the Kubernetes reconciliation model. There's no separate tooling to learn for cluster management. The, dra- the dramatically re- this dramatically reduces the learning curve and operational complexity. Let's talk some real world context. Think about you manage Kubernetes workload today. You don't SSH nodes and run Docker commands. You define deployments, services, and let Kubernetes handle the details. CAPI brings the same level of abstraction to cluster management itself. Instead of scripts and provision VMs and run kubeadm commands, you define a cluster resource and let CAPI handles everything. CAPI itself doesn't provision infrastructure. That's where providers come in. So CAPI provides the API and orchestration logic, but it needs to talk to actual infrastructure. That's what providers do. What are infrastructure providers? Infrastructure providers are the drivers that let CAPI work with specific platform. Each provider implements standard CAPI interfaces but talks to platform-specific APIs. Think of it like database drivers. Your applications uses a standard interface, but each driver handles the specific of PostgreSQL versus MySQL versus Oracle. There are currently over 15 different infrastructure providers, AWS, Nutanix, VMware, Azure, etc. We'll talk about some provider components. So each provider consists of two main components. One is controller and other is CRA. Controllers, these are the Kubernetes controllers that watches for CAPI resources and perform operations. CRDs, these are platform specific custom resource definition that represent your infrastructure. Now let's talk about some platform specific resources. Let me give you some concrete examples. For AWS, we have AWS Cluster, which consists of VPC, subnets, load balancers, AWS Machines, which has EC2 instances, AWS Machine templates. Similar for Nutanix, we have Nutanix Cluster, which consists of Prism Settle configs, networks, Nutanix Machines, which have VM specs, and Nutanix Machine templates. Each provider defines what makes sense for their platform. How does this provider actually work? When you create a cluster resource, you reference a platform-specific cluster resource. Example, your cluster references an AWS cluster or a Nutanix cluster. The provider controller watches these resources. It translates the declarative specs into API calls to the actual platform. For AWS, call EC2, VPC, ELB APIs. For Nutanix, call Prism Central APIs. Common CAPI CRDs that are used by these providers. So these are the core abstraction that all providers use. Cluster represents a complete Kubernetes cluster with control plane and workers. Machine represents a single node. VM could be control plane or worker. Machine set manages a set of identical machine, ensure desired replica count. Machine deployments like a Kubernetes deployment, but for machines, handles rolling updates. If you understand pods, replica set, and deployments, you already understand CAPI models. What does this provider ecosystem has? So this provider ecosystem is one of the CAPI's strength. AWS provider is maintained by AWS. Azure is maintained by Microsoft. Nutanix provider is maintained by Nutanix. Each provider follow the same contract. So switching provider doesn't mean learning everything from scratch. These provides abstraction benefit. The abstraction is very powerful. Your orchestration logic, how you manage cluster is same across all platforms. Only the infrastructure specific detail changes. Example, moving your cluster from AWS to Nutanix. Change the cluster reference from AWS clusters to Nutanix cluster. The topology, the management workflow all stays the same. Let me paint a picture here. You want a 3-node control plane, 5-node worker machine Kubernetes cluster. You create a cluster resource referencing a Nutanix cluster. The CAPI core creates 8 VMs, 8 machine resources for you, 3 for control plane and 5 for workers. The Nutanix provider sees these Nutanix machine resources and calls Prism Central to create these 8 VMs with specific configurations. It monitors the VMs, reports status back to CAPI. CAPI then bootstrap Kubernetes on these VMs, all from a single kubectl apply command. ClusterClass. So ClusterClass is perhaps the most important concept we'll cover today. It's what makes managing hundreds of clusters practical. The problem with traditional API. Let me show you a pain point first. In traditional CAPI, every cluster needs a cluster resource, a QADM control plane, machine deployment, and various templates. If you have 50 clusters, that's 50 set of these resources. Want to change something, you have to update 50 different clusters. It's DRY principal violation at scale. The cluster class solution. Cluster class says define the shape of your cluster once. This cluster class become a template. Creating a new cluster becomes incredibly simple. Reference the cluster class, set a few parameters like version and replica count. That's it. Everything else is inherited from the cluster class. Topology management. Cluster class manages what we call topology, the structure of your cluster. Control plane, how many nodes, what size, which version, workers, how many set of workers, their size, their labels. All of these is defined once in the cluster class. Let's look at some comparison. Traditional CAPI, 100 of line of YAML per cluster, with cluster class maybe 20 lines. The cluster class itself might be 200 lines, but you wrote it once and reuse it forever. Cluster class also supports variables and patches, but that's what makes it really powerful. You can parameterize things with variables. Example, worker nodes count can be a variable. So different clusters can have different counts, different number of worker nodes. You can define patches that modify the topology based on conditions. So imagine you're using a SaaS platform. Each customer get their own Kubernetes cluster. You have a cluster class called customer cluster. When a new customer signs up, your automation creates a cluster referencing that cluster class. Customer name becomes a label. Done. The cluster provisions automatically with all your standard security, network, and policies. When you need to update all customer clusters, maybe a security patch, you update the cluster class. CAPI rolls the update to all clusters automatically. Now let's talk about some cluster class key benefits. Right. So single source of truth. This is about consistency and governance. Security team wants all production clusters to have specific settings defined in cluster class. No more cluster drifts where each cluster evolves differently over time. Simplified updates. This is a killer feature for operations team. Kubernetes 1.28 suppose has a critical CV. Update the version in your cluster class. CAPI automatically rolls the update across all the clusters using that class. It respects best practices, control plane first, then workers, rolling updates. Fast provisioning. Without cluster class, you copy paste YAMLs, find replace names, hope you didn't miss anything, and then you apply. With cluster class, change the cluster name and replica count, apply. We have seen teams go from 2 hours per cluster to 5 minutes. Topology management. The topology concept is brilliant. CAPI understands that control plane and workers are related. It can make intelligent decisions. I am upgrading, so I'll do control plane first. You don't have to orchestrate this manually. Variable and patches. Variable let to parameterize without duplication. Standard production clusters, but no different worker counts. That's just a variable. Patches let you tweak specific aspects with forking the entire cluster class. Version control. When you update the Kubernetes version in a cluster class, CAPI knows it affects control plane and workers. It coordinates upgrades. You are not manually updating multiple resources. So the impact of cluster class, teams using cluster class reports 80 to 90% reduction in cluster provisioning time and 70% reduction in configuration errors. That's not hype. That's the power of abstraction and automation. So let's see cluster class in action. So let's make this concrete with actual YAML you had used. Cluster class structure. Here's the cluster class definition for production cluster on Nutanix. Notice the structure. We define control plane, infrastructure, and worker section. Each section references templates. The control plane section points to a Kubernetes control plane template. This defines how control plane nodes are configured. It also has a machine infrastructure reference. That's the Nutanix specific template. The infrastructure section defines cluster-wide settings. For Nutanix, this is where you specify business central endpoint, credential, network settings. Worker section. Worker can have multiple classes. Maybe you have GPU workers and regular workers. Each has bootstrap configuration, QPDM settings, and infrastructure VM sizing. Creating a cluster with cluster class. Now look at how simple creating a cluster becomes. The cluster resources minimal, metadata, network settings, and a topology section. The topology section is the key. It references the cluster class by name. You specify the version you want, control plane replica count, worker replica count, and that's it. So what happens? When you apply the cluster resources, CAPI, expand the cluster class into all the necessary sub-resources. Create control plane machine, creates worker machines, configure networks, storage, and everything, all from these few lines of YAMLs. Customization. If you need cluster-specific customization, you can add variables and patches to the cluster. But the default is you inherit everything from the cluster class. So here we talked about cluster class, but cluster class is really powerful. It's good, but we still have a problem. Great for consistency, but limited for dynamic customization. So that's where CAREN comes into picture. So CAREN is a framework provided by Nutanix to enable runtime customization of Kubernetes cluster managed with cluster API. It allows dynamic modification of cluster definitions at runtime without altering the base cluster class configuration. CAREN leverages mutation hooks, which intercepts cluster reconciliation to apply changes or patches dynamically to cluster resources, such as machine deployments, and cluster specifications. Instead of editing the cluster class YAML templates directly, mutation hooks apply overlays or patches when the cluster class is being reconciled. This maintains the integrity and the reusability of the base cluster class while allowing customization for specific deployments. Let's say example, dynamic network configuration. Suppose an organization wants to inject specific network proxy settings only for cluster deployed in certain regions. Instead of modifying the base cluster class for all region, a CAREN mutation hook can detect the cluster location and inject the necessary proxy environment variable dynamically into machine templates. Runtime version overrides. During cluster upgrades, CAREN hooks can dynamically modify Kubernetes version, field, per cluster, or machines class without changing the core cluster class. This allows controlled experiment rollout of new version in select clusters. So cluster topology reconciliation. This diagram illustrates how the cluster topology controller works within the Kubernetes API server to reconcile cluster topology. The controller receives cluster reconcile events and fetches the cluster topology. It computes the desired state and generates patches which can be inline or external. These patches are applied in a loop until the cluster desired state is reached. This process ensures clusters are kept in the desired configuration as declared by users or automation. Let's say if a cluster administrator wants to add a new control plane node, the controller detects a change in the cluster spec, generates a patch to add node, and reapplies until the actual cluster state includes the new node. This automation reduces manual intervention. So this is an infrastructure control and cluster lifecycle events. This slide shows the lifecycle of a control plane and worker nodes in a Kubernetes cluster managed by Cluster API. It details a sequence of cluster creation, upgrades, and delete events. Hooks are called during various phases, such as initialize, create, upgrade, and delete, providing extension points. The lifecycle ensures smooth transition and consistent cluster state management during these operations. References is made to the Kubernetes Cluster API Lifecycle Hook documentation for implementation details. Let's say during a cluster upgrade, hooks allow injecting custom validation or backup steps before the control plane upgrade begins, ensuring operational safety. For instance, a backup hook might capture a set snapshot before updating. So key takeaways for this, Cluster API provides a declarative approach to managing Kubernetes cluster lifecycle. ClusterClass acts as a blueprint, ensuring consistent and repeatable cluster creation. CAREN adds a flexible layer to adapt the cluster specific for real-world use cases. Together, these components standardize cluster management while preserving flexibility. This approach simplifies operating Kubernetes cluster at scale with predictable outcomes. So let's say using cluster class, an organization can define a standard 3-node control plane template. Every new cluster created from this blueprint consistently follows the same tested configuration. CAREN then enables patching specific cluster settings like region or instance sizing dynamically based on developing environment.
So, hi team. This is Kshitij, and I work at Nutanix in a team called Nutanix Kubernetes Platform, where we work on providing a managed Kubernetes platform solution, as well as uh, features such as cluster management, application management, and fleet management. So, till now, you would have gotten some understanding and idea about the cluster API, the foundation of the entire Kubernetes, and the CAREN, which is required to install the components to make the cluster actually functional, right? So those are the ones that we call unnecessary day zero operations. And coming to this particular problem that we'll be going to discuss going forward, right? That your cluster is up, your cluster is functional. What about applications and what about data operations? So from these problem statement, the actual requirement that comes are as follows: that how do you configure your platform to handle multi-cluster configurations or managing a fleet of clusters? A fleet of clusters typically has a management cluster, which is the sole authority of what is going to be deployed on what workload cluster and in what form and shape. The second key requirement is the drift detection and the reconciliation. So as the platform administrator, you would want your clusters not to drift from the existing installation, and they should be always in the consistent with the desired state. Third thing is the secret management and how to propagate, distribute, secure the secrets which are required across the clusters. And fourth thing is multi-tenancy and isolation, right? That how do you provision clusters in such a way that one org or one team of your company is completely isolated and secure and obsolete from the other, right? So we'll be focusing on certain things that we do here and certain components that we have used in our platform to make and meet all these requirements. So the key highlight here is the GitOps. So GitOps is nothing but the state or the declarative state of your Kubernetes cluster and the applications coming via a Git source. And that's how the term GitOps has been evolved. And this is a true essence of the Kubernetes, that the entire design is declarative, and for applications as well as the clusters and the configurations and the Helm chart values, we follow the same, right? We define the target state in a Git repo, which is what acts as a source for your cluster to watch on and reconcile. So pursuing the same idea of the GitOps, we are today going to talk about the Flux CD, which is one of the main and the trusted GitOps provider. There are others like Argo CD, but in this particular session, we'll be talking about the Flux. So as this diagram can be understood and can be interpreted, there are multiple components and multiple actors here which are involved in this entire process. So let's go and see what each of the actor or the process does here. So in the top, we have the platform team and the platform ops, people who are responsible for making changes and for deciding that an application now is going to be deployed on my CI cluster or my pipeline with certain number of replicas, which is like with any configuration, right? So what this guy does is actually opens a pull request to the desired Git repository where all the configurations and the applications are stored. Once the changes are merged to that Git repository, the Flux and its magical components come into picture. So Flux has a component called the source controller or the source reconciler, which is designed to work on all possible kinds of sources. In this case, that source is a GitHub repo. And what the source controller will do, it will, in its period or whenever there's any new write that happens on the Git repo, this will wake up and this will actually reconcile whatever is mentioned here in the GitHub state, and it will try to act on that and will try to apply that on the cluster. So here, if you see, the management cluster has a Flux and Flux has a source controller which keeps on watching this GitHub repo and will keep on looking for the changes. And as soon as it figures out that for a particular application A, the number of replicas are now increased, it will pass on the same message to various other components running in the cluster who will make it happen. So Flux or this Git source controller, they are not a component on its own. It is the entire Flux is a set of components who work in tandem to make things happen for your cluster. In further discussion, we'll be going a little bit deep on each of these controllers and what they do and how are they relevant in the Flux ecosystem. Right. So highlighting the key components here for the problems or the for requirements that we discussed is Flux CD. We have already gone through it. The Helm, your package manager, your release orchestrator, your one of the component which is actually handling what resources and what specifications with an application would be deployed. There's a tool called Kustomize that we'll cover later, and it is really a fascinating tool, and it helps a lot with doing the declarative stuff in the most predictable way. And then we have Istio, and Istio is very popular. It's a service mesh, and it's just provides entire service mesh capabilities for all the applications running on cluster. Your workload can use Istio mesh, and they can just worry about um, providing their functionalities and feature, and not about how the applications are going to be accessed and who would trace it and other things that come with it. And then we'll cover one key component called ESO, and it's a relatively new component compared to all others. And ESO is called external secret operator. And what we will go through here, the use case of secret synchronization and the secret management. So our entire platform or the entire problem statement will just use these 5 components to begin with. Just keep in mind that these are not exhaustive. There are so many other components which runs in tandem or in parallel with these components to make entire management a stable thing. But these 5 are the most essential ones in this context. So now going a bit deeper on the Flux. Flux ecosystem comes with 4 components, which are really the backbone of the entire magic that happens. So we've already talked about the source controller, and source controller is a custom resource. Its custom resource is defined by Flux, and the source controller can reconcile or can watch over multiple types of sources. So it could be a Git repo, it could be a Helm repo, it could be a S3 bucket, and the latest, it could be an OCI repo, which is the industry standard going forward, right? So you point your source controller to the source where you want your cluster to be in sync with. After the source controller, we have the customized controller. So customization is really a client operation where your manifests are aggregated and there are certain features that this customization process provides, and your manifests are applied through those features and they come in their final shape and form. So your customize could generate stuff for you. It could create secrets, namespaces, config maps where before your main application is getting installed. It provides more features such as patching and overlays where you do the patching and overlaying required based on the conditions. Like, for example, if this is a prod cluster, then the replica count and the image should be used something different than what your staging cluster is using. So this customized controller provides all those benefits, and ultimately it aggregates all the resources you have. And these resources usually are in form of Helm releases, because actually anything that gets deployed or installed on the cluster is via Helm. So ultimately, the final shape and form of Helm releases are rendered. And from there, your Helm release controller takes over. It watches on the Helm release resource and it again tries to reconcile that on the cluster, right? So what these three components does is basically decide what to deploy, how to deploy, and like when to deploy and whether it could be deployed or not, right? There's a fourth component here, which is also very much required in this entire domain, which is called notification controller. And the notification controller acts as a final notifier or the alert broker kind of guy, which tells you or your administrator or your developers that whatever they wanted to do via the source that they have defined is done or is not done. So notification controller also is a way to inspect what is happening in the cluster without going inside the cluster. Now a bit about Kustomize. Kustomize is a Kubernetes native configuration management tool, and it purely works on the declarative principle. And what it provides in the real world use case is the base and the overlay architecture and the patches. So here in this particular example, you can see that there is a, in the base directory, there's a customization.yaml file, which would point to the deployment.yaml, service.yaml, and the config maps.yaml. Now in your overlays, what you want to do here is modify or patch all of these YAMLs based on the environment that they are going to be applied against. So for example, in the development, in the overlays development, so for a development cluster, your customization will point to the replica patch and the dev config map. And in your replica patch, you will refer to the source that to create this YAML, I'm going to take the base deployment.yaml and I'm going to patch my replica count on that. Similarly, for the dev config map.yaml, I'll take the config map.yaml defined in the base resources. I'll update certain things which really make sense in my development environment, and I'll create this config map for that. Similarly for staging, similarly for your prod. So what happens is you don't have to specify the common elements in all these YAML files, right? So all of them gets bulkier. Instead, what you can do is you select what are those elements or those parts of the YAMLs which would be applied for all the resources, and then you do the overlays via the customization process. The next key component is ESO, and ESO is external secrets operator. What it does is, so now we are going to discuss the ESO, and ESO, what it does is it operates or it like automates the secret management for you. In this diagram, what you see here is your ESO operator, and these three boxes are basically different components or different, you can say, aspects of it, right? So in this particular example, your external secret operator is pointing to an AWS or a GCP or a HashiCorp Vault source, and it is tuned to fetch the credentials from your upstream vaults and provide to the workspaces or the namespaces or the applications running in these namespaces syncing from upstream. So what happens is, or what are the benefits is that you don't have to keep your secrets inside the Git or inside any other source, right? You can at runtime or at the time of consumption, you can really tune this to basically fetch the secrets for your workloads to be configured, or whatever secrets those workloads require, and provide them in the real time. One more thing that it helps us is that if all of this is being maintained by a DevOps or the SRE, that then like as soon as your upstream secrets are rolled over, you do not have a way to automatically reconcile that. So somebody would need to step in at the time of failure, that failure is caused by the secrets and I need to update or refresh the secrets. So this operator, again, it lets you watch over your upstream source, and it lets you reconcile that based on the time that you want. If you want it to look for any change in secrets in 1 hour or in 1 day or a week. So it could be tuned according to your use case or according to the policy where your organization keeps refreshing the secrets in a certain amount of time. Continuing with ESO, we have a very particular use case of ESO, which is called push secrets. So in the deployment model where there's a management cluster and there's a workload cluster, and there are a group of workload clusters to be managed from the management cluster. This push secret, what it does is you keep your secret. For example, all of your workloads or all of your clusters would require pulling charts or the images from the OCI repository. Now, instead of you configuring this kind of secret for all of your workload clusters, what you can do is that you can have the management cluster store it. And as soon as you create a new workload cluster, this operator pushes the secret from your management to the workload cluster. As soon as your OCI credentials are changed, again, you change your source, right? You change your credentials on the management cluster, and this push secret job or the reconciler will immediately make sure that this gets propagated to all the workload clusters. So this is really beautiful in terms of how it makes the secret management an easy job, and you don't have to keep looking for what secret is going to expire and how to sync them. So just quickly glancing to the YAML, there is a secret defined in this YAML, which is called Pikachu, and the name is push secret example. So this is where your secret is defined. This secret could be anything, right? It could be a basic auth, it could be a service account token, it could be your API keys. Then you define a push secret kind, and push secret kind would do a secret store ref where you can provide the list of secrets stored to push secrets to. So in the management and the workload cluster, the secret store ref would be pointing to one of the ref your workload cluster is having. And then you define the data and the time where it would need to push the secrets to. So this is pretty elaborate, and everybody can just go through it and just use it how your organization or your use case requires. Okay, a bit too much of the slides. So in summary, what we have here is that, like, in this small demo, what we wanted to showcase is that we are using CNCF projects for whatever we are building here, and GitOps is the fundamental piece of it. And all the modern requirement of providing the multi-tenancy and providing the isolation, the RBAC, and providing your different organizations or different teams a different kind of environment, all of it is possible through GitOps, and it is a single pane of glass for managing multiple clusters in the most declarative way. So at the end of it, I just want to do a quick demo about how whatever I have talked about, how does it look in the actual cluster. So just bear with me. Okay, so we started with Flux, and we can check that in the Flux, we have what all components that we have in the Flux. So if you see here we have the Helm controller, the source controller, the Kustomize controller, and your notifications image controller. Right? Each of these controller runs as a pod, and they are configured to watch certain custom resources that gets created throughout the process. So once the Flux is installed, the Flux bootstrap is done by Flux CLI. It is available on the Flux documentation, the official website. And as soon as Flux bootstrap is done, all these controller gets deployed and the pods come up. And now let's check one of the sources that we have, right? So OCI repository is one of the source that we could use. There could be Helm repositories as well. There could be Git repositories, and there's 3 buckets. And if you see here in the OCI repository, the kind is always OCI repository. And this says that there's a customize label here, and there's a name of that customization is called centralized Grafana, for example. So the source controller, what will it do is it is provided an URL that go to this OCI repo and keep checking for every 10 minutes if there's any new thing to ingest or to reconcile. So this is how the spec is defined for this source controller. And this is pretty similar or pretty common to all the sources that are available with the Flux. And here you can provide your secrets that this particular controller or the job has to use to actually talk to this OCI repository. So coming to the source controller, it just watches a particular path in the OCI repository and waits for a new change to come or a new tag or a new label, right? After the OCI repository source controller resource, let's watch a customization resource. And let's take the same example, the centralized Grafana. And here, if you see, there's also a customize toolkit Flux CD label that this is also generated by a particular customize. And there are certain other labels that are added here, which could be added using all the customized features. And in the spec here, again, it's an interval where it needs to see that after every 6 hours, it needs to check, like, does it have to generate a new customization? Is there any change that it needs to reconcile? Other than that, it provides certain patches and other operations. So it provides that you can do an addition operation on the path metadata.label, and you can add this particular label. So this particular label will be added to the customization resource of the Helm release type. So it's saying that there is a centralized Grafana Helm release. Annotate or label it with this particular label. Similarly, there's an operation called add, and it is also providing certain path where a value needs to be added as true. So this is what we were referring to in the overlay or the patches operation, right? So this is an operation add, this is an operation replace. Similarly, there is operation add and replace, where you tweak your YAMLs to a very certain nitty-gritties, right? Once the customization is done, let's look at the Helm release, and let's look for the particular Helm release. So if you see, the Helm release is currently labeled with what we have seen in the customization is that it's managed by an app called app deployment. And in the hem release, it only has the reference to a chart, that what particular chart this hem release is going to deploy. And there is an interval like all other resources. There are conditions for install that if the CRDs don't exist, create or replace the new CRDs. If the namespaces where the hem chart is going to be installed is not there, create the namespace. These are the number of retries before it keeps up and says that cannot make this hem release ready. And similarly, you can define upgrade strategy, the install strategy, and you can define from where the chart is going to take its values. So you can point certain config maps where before actually being applied, your values would be taken from there, and Helm applies a three-way patch. It checks what the current values that it has, it checks what are the required values in the config map, and it applies a patch and then installs the Helm release. So here, if you can see, Helm release is succeeded once it is successfully applied. So to summarize, this is what we wanted to cover for today's topic, and it was really fun doing this presentation for you guys.